Hi everyone, thanks for attending my presentation. My name is Sheng Guan. This is a joint work with Hanchao Ma and my supervisor Yinghui Wu. We all come from Case Western Reserve University. This work is about robustifying node classification under link perturbation. We call it RoboGNN. If a GNN-based classifier M is trained on graph G, then M can be sensitive under a set of link perturbation posed to G. For example, node 5 in this graph originally is predicted correctly as blue color class. However, it is predicted incorrectly as white color class due to malicious adding edge attack. This desires the need to protect the status of node pair 1,5 in order to mitigate the impact of adversarial attacks during the model learning. Such vulnerability can bring severe consequences, which leads to false predictions or malicious recommendations in applications such as online fraud detection, talent recommendations, and co-selling recommendations, to name a few. Hence, it is desirable that the robustness should be ensured for targeted nodes of interest. At the same time, a small set of auxiliary links should also be protected. We introduce a novel and practical problem that takes the input, a perturbed graph G, an input model M, a set of targeted nodes Vt, a set of vulnerable links EP, and a budget size P. The output is a triple. That is an updated graph G prime, an updated model M prime, and the protection link set delta L. We introduce P theta robustness, which characterizes the robustness guarantee of a GNN-based classifier M, considering all the possible graphs obtained by applying perturbation of up to P links from the vulnerable set EP. We call them admissible graphs. To be specific, for a single node V, our goal is to verify whether no admissible graph can change the prediction. If there exists no adversarial example that leads to a change in the prediction to some other class C, equivalently, its worst-case margin is larger than 0. We say V is robust in this case. If graph G model M is robust for at least theta fraction of targeted node set Vt, we see Gm achieves P theta robustness. To verify a pair Gm achieves P theta robustness is an NP-hard problem. Meanwhile, P theta robustness has a monotonicity property, which tells us that it's desirable to compute a smallest set of links, delta L, that should be protected. We first develop an algorithm, MinProtect, to compute the smallest protection set, delta L. It applies a traversal-based greedy selection strategy and is optimized by an approximate PageRank computation. This algorithm firstly estimates and selects the next target node that is most likely to be robust upon current delta L. Then it applies BFS traversal to identify and augment new links, updating delta L. In the end, it verifies whether GM achieves P theta robustness or not. Next, we present RoboGNN, a co-learning framework that interacts model learning with graph structure learning to robustify an input model M towards P theta robustness. Using real-world benchmark graphs, we show the effectiveness of RoboGNN. We firstly verify the improved robustness, in turn significantly improves the accuracy of given input models. Meanwhile, RoboGNN can be extended as end-to-end learning, which achieves the best performance among all baselines due to its robustness guarantee. RoboGNN also effectively suggests recovered adjacency matrix, which can be directly reused to train other GNN models from scratch more accurately. The code of RoboGNN is available in the GitHub repository. Thank you for listening.